So we've got this question here. We're covering internal forces right now. This problem right here is just an internal force problem, but you'll also get into diagrams pretty soon here, which are almost a little more important than just internal forces by themselves. So I'll go ahead and read this out. It says, determine the normal force, the shear force, and the moment in the beam at sections passing through points D and E, and then point E is just to the right of the 3 kip load, which kind of means that it's not right under it, it's a little bit off to the side there. So what we want to do first is we want to find what our support reactions are of this entire beam. And so in order to do that, we're going to want to split it off into, if you guys could notice, there's like a little hinge here. And so because of that hinge, we can't just solve for A and all the reactions at C by itself. We're going to have to draw 2 separate free body diagrams for this beam. Hi. So we'll go ahead. I'll draw them off to the side up here. So first we've got A, B, and at A we've got a force acting upward. Label it AY. And then at B, it's a pin connection, and these are not 2 force members because they both have external forces on them. So we're going to have something like BY and BX. And I just drew them positive at first, just convention-wise. And then we'll go ahead and draw the distributed load in there as well. It's 1.5 kip per feet. And then dimensions of this. I'm not going to worry about splitting it out for point D here. We're just going to go ahead and write the whole 12 feet there. So that's our left side of this hinge here for our free body diagram. Next we'll go ahead to the right side. And at this right side, if you saw these reaction forces at B, BX, and BY, they'll also be present over here. They'll just be in the opposite direction. BY and BX. And then right in the middle, we've got 3 kips acting downward. And then C is fixed into the wall. So we've got a CY, a CX, and then a moment from C. So does anybody have any questions about these so far? Hopefully they're pretty straightforward at this point. I'll go ahead and draw in the dimensions here as well. We've got 4 feet and 4 feet for that one. So now we want to solve for what AY is and then what all the reactions at C are. So we'll go ahead. I'm going to start with this one up here. I'm going to go ahead and start with the moment about point B. So we're going to take the sum of the moments about B to find what AY is. So first we're going to have this distributed load, and the total of this distributed load is going to be the 1.5 times 12 feet, and then divide it by 2. So that's what our distributed load is. And then to get the moment on a triangular distributed load, the center of it or whatnot would be 1/3 from the taller edge. So it'd be about 1/3 of the distance over here. So from B, it would be 4 feet over, because that's 1/3 of the 12 feet down here. So we've got that, and it's going positive because it's going to be pushing down on it in a counterclockwise direction. And now we're going to have AY, which is going to be pushing in a clockwise direction, so minus AY, and it's 12 feet away from B, so we'll do that. And those are the only 2 forces that would be causing a moment, so we can set those equal to 0 on that one. And when we solve for AY, we get that AY is equal to 3 kips going up. We'll sum the forces in the Y is going to be equal to our AY, which is 3 going up, minus our 1.5 times 12 divided by 2, and then our BY. And when we solve for BY, we get that BY is equal to a positive 6 kips. And then some of the forces in the X. is just going to be equal to Bx, which is 0. So these are our reaction forces on the left side. Now we want to get the reactions on the right side for C. We'll go ahead and do that. We'll take the sum of the moments about C, and we've got to include the moment of C. And then we also have to include our 3 kips times our 4 feet. And then we're also going to need to include our By. By, and that's going to be times 8 is equal to 0. And we have that By is equal to 6. And so we can substitute that in pretty easily. And we'll get that MC is equal to 60 kip feet. And it's going to be going in the clockwise direction because we got a negative number. Next, we're going to sum the forces in the y. And we're going to have our By, which is going to be going downward, and it's positive 6. So negative 6, and then minus 3, and then plus Cy is 0. So Cy is therefore equal to 9 kips acting upward. And lastly, we'll take our sum of the forces in the x. And when we sum our forces in the x, we're going to get negative Bx plus positive Cx is equal to 0. And we got that Bx earlier was already equal to 0 over here. So we're going to get that Cx is also equal to 0. Any questions so far about this? It's just kind of solving for support reactions, so hopefully you guys know this stuff by now. This is where we're really going to get into the new stuff, the internal forces. So what we want to do is we want to use all this information we just learned to solve for the internal force here at D. So do you guys know how to kind of expose your internal forces? Was that kind of a... Yeah, so you're going to make a cut at the point that you want to find the internal forces at. So right here at D, we'll start at D because I think it's a little maybe simpler. But right here at D, we'll make a cut here. And we'll draw a free body diagram. And I'm going to draw one of the left side because there's a lot less going on to the left of D than there is to the right of D, because we got more of this distributed load and the hinge and all of that. I'd rather just mess with this simpler side. So let's write down here, left of D. So when we do that, we'll draw this little section in here. This section is going to be 6 feet long. We're going to have our reaction at A, which we found to be 3 kips going upward. So we'll draw that in. And then our distributed load is going to be going up still in a triangular fashion. But one thing to note is this one's pretty simple, but when you cut through a distributed load like this, the height of it is going to be different. And so because we cut through it about halfway through it, our height is going to be half of what this is. So instead of the 1.5 kips that they give us, it's going to be 0.75 kip per feet. And if this weren't halfway, then you'd have to essentially take this little distance here divided by the entire distance and then multiply it by the height here. So for example, this would be 6 feet divided by 12 feet, which is 1/2, and you take that 1/2 times that. It's kind of basic geometry type stuff, but I don't blame you if you forgot it, because when I took this class, I definitely forgot that type of stuff. So next we want to draw in our internal forces. And this is one thing where you just have to memorize it. There's a certain convention on how we draw our internal forces, and you really can't draw them in another way, or else you'll just get the opposite answer. So for our left side here, shear is always going to be going down. Our normal is always going to be pointing out, and then our moment is always going to be pointing that way. So it's kind of hard to explain why, but the way that I like to kind of visualize with the shear is, let's say that we have these two pieces. The internal forces are showing in here. On this side, you're going to have the shear going this way, and you're going to have the shear going that way. With this drawing here. So the way that I like to think about it is that it's going counterclockwise, if that makes sense. It's kind of a weird way of remembering it, but that's just what works for me. So you just have to remember that it goes counterclockwise. So if you're ever on the left side of a cut, the shear is going to be pointing down, and if you're ever on the right side of a cut, the shear is going to be pointing up. And then normal force is pretty easy, is that it always just points outward. We just assume it to be in tension and positive that way. And moment is kind of interesting. One way that I was taught moment is, I'm going to draw 3 little sections here. So let's assume that we make a cut here and a cut here, and there's a little section in the middle of the cut. Well, we essentially want to turn the moment of the cut in a way that almost makes it smile, if that makes sense. So it curves down, makes a smiley face. So therefore, you'd be applying moments to it that way. And so when you apply moments to it that way, you can look and see, using opposite and equal, that the moments on the other sides would be curling around them like that. So those are just some tricks that I use to memorize them. There's kind of not too much logic to them. It's just something that you have to know. But hopefully that helped. Does that help you guys? Okay. So now that we know kind of our conventions with drawing those, we can go ahead and solve this. This is essentially now just another equilibrium problem, basically. So we'll go ahead and start with our sum of the forces in the x. So sum of the forces in the x, looks like the only force we have acting in the x is the normal force, and that's going to be equal to 0. That's one of our answers. I'm going to draw a little subscript down here for ND, so the normal force of D. I'm going to go ahead and put subscripts into all of these. So the normal force at D is equal to 0. We'll go ahead and sum the forces in the y. And so we do that. We're going to have our 3 kips acting upward. We're going to have this distributed load acting downward, so it's going to be our 0.75 kip per feet times 6 feet, and we'll divide that by 2. And next we've got our shear acting downward, so minus V, D. And those are the only 3 forces in the vertical direction. That's going to equal 0. And doing this, we end up getting that VD is equal to 0.75 kips. And with internal forces, you don't want to draw the arrows with them. We already have our convention on how we draw the arrows here. And so when you come up with your answer down here, you just leave it in positive or negative. You don't draw in whether it's going up or down, because if it's going down on this side, it's going to be going up on the other side of the cut. So it gets kind of confusing. So just using our convention of how we draw these, just write if it's positive or negative. And let's see, we'll go up a little more. And lastly, we'll take the moment about this cut here. So the sum of the moments about the cut is going to be equal to MD, and then we're going to have our 3 kips acting in a clockwise, so minus 3 times 6, and then we're going to have this load going in a counterclockwise. So plus 0.75 times 6 over 2, and then our distance is going to be 1/3 of the distance, so 2 feet. And those should be the only forces causing moments. And when we solve for MD, we get that it's equal to 13.5 kip feet. Does that make sense to everybody? You guys have any questions about that so far? All right, we'll go ahead to our other side. Let me section that off. So now we're going to be looking for the internal forces here at E. And it gives us that E is just to the right of the 3 kip load. And basically what that means is if we were to make a cut right through E, the 3 kip load would not be on that little section there. So that makes it kind of easy for us. So we're going to go ahead and look at the drawing for that section there to the right of E. So we'll go ahead and draw this in. We're going to have our reactions at C. So we got that the vertical reaction is 9 kips. There is no reaction in the x direction, Cx is equal to 0, so I won't draw that in. And then we'll go ahead and draw the moment in, which we got as 60 kips going clockwise, or 60 kip feet going clockwise. And then at E, we'll also have internal forces. We'll have the shear going up as we look at our convention over here. I'll label that as VE. We're going to have our moment kind of curling around that way as we show in our convention there. So ME, and then I'll go ahead and draw in the normal force, which is always going to be pointing out, and that's NE. So we solve for these just as we did before. We'll go ahead and draw in the dimensions here, which were given above as 4 feet. So we'll go ahead and solve. I'm going to start with the sum of the forces in the x again. So sum of the forces in the x is going to be equal to our negative NE, and it's negative because it's pointing to the left. And there's no other forces, so it's equal to 0. And we basically just get that the normal force is equal to 0 here. We're going to go ahead and sum our forces in the y now. That's going to be equal to VE plus our 9 kips from the reaction, and that's going to be equal to 0. So VE is therefore negative 9 kips. And again, no arrow, just the negative sign. And then we're going to sum our moments about the cut. So our moments about the cut, this is going clockwise, so we're going to have a negative ME. We have this one going clockwise as well, so minus 60. And then we have this 9 kips pushing upward in a counterclockwise form. So it's going to be plus 9 times 4 is equal to 0. And so when we solve for that, we get that ME is equal to negative 24 kip feet. Okay. And those are all the things that we needed to solve for in this problem. We've got our normal forces, which both of them end up being 0, and then our shear forces and our internal bending moment. And as far as I can tell with the problem, that's all they were asking for at D and E. So we should be good to go on that one. So now we're going to get into kind of how you would solve for, or how you would go about solving for the diagrams, the shear and the moment diagrams. So there's a couple of moments that you're going to, or a couple of ways of how you're going to learn this. I'm going to teach you the first way, which is more time consuming and not as fun as the other way, but I feel like it's something that's important for you guys to learn. And I don't think you guys have covered it in your lectures yet. So what we're essentially going to be doing, as I wrote in the question here, is we're going to find the shear and the moment, which shear is V, and the moment is obviously M, for any point left of A, between A and B, and to the right of B. So that's kind of confusing how I asked it, but essentially what I want is I want a formula right here for what the shear and the moment would be before A, and then I want another formula for what the shear and the moment would be between A and B, and I want a third formula for what the shear and moment would be at the right of B. And using those formulas, that's how we're going to go ahead and draw our diagrams. So it sounds kind of freaky when I start talking about solving for formulas and stuff like that. It's ultimately what we just did on our regular internal force problem, except now instead of set distances, the distances are going to be a range. So the first thing we're going to want to do is solve for the internal forces at A and B, which I already have done. I don't need to waste your guys' time doing that. So at A, we are going to have our 80 kips acting upward. And at B, we are also going to have 80 kips acting upward. And there was no lateral force on this, so there's no force from B in the X. And that's part of the reason why you're going to end up finding out that you don't really have to worry about the normal force as much as you have to worry about shear and moment. On the exams and stuff, there will be a lot of questions about shear and moment diagrams, but there really aren't too many about normal force. So you'll end up finding out that it's not quite as important as the other two. It's still important, a good thing to know, but not as vital right now. So, using these, we're going to want to find the formulas here. So to find the formulas, we're just going to take cuts off of these like we would normally. So I'm going to start with left of A. And so when we start with the left of A, we're going to draw, let's say we have an imaginary cut kind of through there. Let's see. We'll go ahead and draw this in. So here, we're going to have 20 kips acting on the edge there. And then, if you can see kind of along this cut here, there aren't going to be any other forces acting along it. So we can go ahead and draw in our internal forces, which again, convention shows us that shear is going to be pointing down, and our moment is going to be going around this way. And I'm not going to go ahead and draw normal force. We know it's going to be 0 because there's no lateral forces on this at all. And the last thing we want to draw is our distance. And this is where it gets a little different, is instead of drawing like a set distance, like the 15 feet here, we have a range of any distance along this here. So we're going to go ahead and label this distance as x1. So what we want to do is just use our equilibrium equations just as we would normally for this one. So we're going to go ahead and solve for the forces in the y. And so summing for the forces in the y, we're going to get our negative 20 kips going downward and our negative shear, because it's going downward, those are going to be equal to 0. And we're going to end up finding that shear is equal to negative 20. Now that's pretty easy. That is what our formula is going to be. It's just that it's a flat negative 20. There is no change with any distance or anything like that. Where it gets a little weird is with our moment forces here. So we're going to go ahead and sum our moments about the cut. When we do that, we're going to have M for our moment here. And then the only other thing, shear is not going to cause a moment here because it's acting on the cut. So there's no distance. We're going to have our 20 kips, and it's going to be going counterclockwise. So plus 20 times x1, that's our distance, and those are going to be equal to 0. And so solving for that, we're going to get that our moment is going to be equal to negative 20 x1. And those are our two formulas for any cut along here to the left of A. Next, we're going to want to find what our formula is here in between A and B. This is where it gets a little bit trickier, but nothing we can't handle. So we're going to say between A and B. So between A and B, we'll draw like another imaginary cut somewhere along there. And if we draw in our free body diagram, all right, we're going to still have this 20 kips acting on the left, downward, 20 kip. And then at A, we're going to have our 80 kips acting upward. And then also at A is where our distributed load gets started. So we'll go ahead and draw that in up until the edge right here. And we find that to be a 4 kips per feet. Okay, and now all that's left is our dimensions. So the dimension from our 20 kip to our 80 feet, or from the edge to where A is going to be the 15 feet that we have up above here. Our distance from the edge to here, we don't really know. It's going to be a variable. So we're going to label this one as x2. And then we're also going to want to draw in our internal forces. So shear is going downward. Our moment is going to be curling around like that. So these are our distances here. Now we can get into our equilibrium equations. So we'll go ahead and sum our forces in the y. So summing of the forces in the y, we're going to have negative 20 from that, a positive 80 from A, and then I'm going to go ahead and write in our negative shear. And then this is where it gets a little tricky. So we've got our distributed load, but we don't have a set distance for it. So we're going to have to find it some other way. Or not some other way, but we're going to have to figure out what this distance is. What this distance is essentially going to be is we know what this 15 feet is here, and we know the total length. The distance of this is essentially going to be our total length, x2 minus 15. So hopefully that's not too difficult to see there. But we're going to have acting downward, it's going to be our 4 kips per feet times, and then the distributed load is going to be acting over x2 minus 15. And those are going to be equal to 0. And we're going to go ahead and solve this out for our shear. And we end up getting, well, I'll go ahead and simplify this a little bit. We've got negative 20 here, we've got 80 here, and then negative 4 and negative 15, they'll multiply and end up being 60. And when we get that, this is end up going to be 60, and then another 60. We're going to have 120 minus 4x2 minus v is equal to 0. And so we're going to get that our shear is going to be equal to 120 minus 4x2. That's our formula for that. And now we're going to go to the sum of the moments. So the sum of the moments about the cut, we're going to have, first off, we can write in our moment m here. And then I'm going to go for the simpler thing. So we're going to have our 20 kips acting in a counterclockwise direction, so 20 times, and that distance is just going to be x2. And then we're going to have our 80 kips going in the clockwise direction. And again, this is the same distance. It's going to be x2 minus 15. And lastly, we're going to have our distributed load, which is going to be, again, it's going to be acting in the counterclockwise direction, so positive. And it's going to be our 4 kip per feet times the distance that it is, x2 minus 15. And then as far as the distance where it's acting, we know that it's going to always be halfway, right in the middle of the distributed load if it's going to be an x shape like that. And so halfway through is going to be this x minus 15 divided by 2. All right, and those are all the forces that will be causing a moment, so that's going to equal to 0. And then this is where it gets a little bit difficult on a lot of things to add here. I'm going to go ahead and simplify it down here, so it's going to be 0 is equal to m plus 20x2 minus 80x2. Then negative 80 times 15 is going to be plus 1200. And then doing this here, we're going to end up getting 2x2 squared minus 60x2 plus 1650. And using all of that and condensing it down and solving for m, we find that m is going to be equal to negative 2x squared plus 120 times x2 minus 1312.5. And that's kind of an ugly number, I'm going to be honest with you. These formulas aren't the most, I hate to say, I guess, appealing or whatever. They're kind of messy and gross. But they work and they get the job done. So we've got our formula for in between A and B. Lastly, we're going to want to find what it is for some random cut to the right of B. And so to the right of B, we're going to go ahead and take this entire section all along here. We're going to start from the left end and go to the right of B here somewhere. So we get that. We're going to draw in our forces. We've got our 20 kips acting here. Our 80 kips from A acting there. And then we're also going to have our other 80 kips from B acting upward. And we're going to have the distributed load along here. And that's going to be 4 kip per feet. And then here at the cut, we're going to have our shear force going down, and then our moment force curling up like that. And then we're going to want to draw in dimensions lastly. So we've got between here, 15 feet. Between here, it's 30 feet. I'm going to also draw this whole distance as 45 feet. And then all the way, we'll label this total distance from the left end to the cut as x3. So that's our free body diagram that we have to work with. And we'll go ahead and just use our equilibrium equations like we're used to. And so we're going to go ahead and solve for the forces in the y. Solving for the forces in the y, we're going to get our negative 20 kips. We're going to get 80 kips acting upward, another 80 kips acting upward. We're going to get our negative 4 kips, and this time we have the full 30 feet, so we can just write it as negative 4 times 30. And lastly, we're going to get our shear acting downward, so negative v. And that's all going to equal to 0. And what we're going to get is we're going to get shear is equal to 20 kips, and that's going to be positive. And now we're going to take the sum of our moments about that cut. So the sum of the moments about the cut, we're going to have m, and then we'll go just along from left to right. We're going to have m, and then 20 kips times x3 is our distance there. We're going to have negative 80 kips times, and this is going to be x3 minus the 15, because we're going to go all the way down here to x3 and subtract 15 to get to where that is. x3 minus 15. We're going to have the other 80 kips, and that's going to be x3 minus 45. And I'm going to have to write this on another line, so bear with me there. We've got these, and then we're going to have our distributed load, which is going to be positive 4 times 30. And then the distance again is going to be halfway in between this distributed load, which is going to end up being 30 from the left end. So we're going to have x3 minus 30 for that. And all of these are going to equal to 0. And so when we calculate this one out, this one gets really ugly. We're going to have m plus 20x3 minus 80x3 plus 1200 minus 80x3 plus 3600 plus 120x3 minus 3600. And all of that is going to be equal to 0. And I only wrote that out just so you guys could see what it would look like expanded out like that. And then we're going to combine like terms and solve for m. We're going to get up end up getting that m is equal to negative 1200 plus 20 times x3. And that's our formula for the moment there. So those are all the formulas that we're going to need for our diagram here. We've got all of these. So we can go ahead and draw those in. Do you guys have any questions about how we found those, by the way? It's one of those things that if you kind of get the convention on how to solve for internal forces, you'll be able to solve for these. It's the same thing, but instead of having set numbers, it's just variables. So it's a little bit tricky, but next we're going to go ahead and draw this in here. And so it says, draw the shear and moment diagrams for the beam. This is the same beam that we had before. And now we just need to use the formulas that we got. So, you guys don't mind, let me get a ruler real quick. An architect scale. I'm going to go ahead and draw straight lines down here. Now the reason I'm drawing these straight lines is because these are where our changes in our formulas are going to be. Because as you guys saw earlier, our formulas change when we apply different forces to our beam. So we're not going to have a set formula for shear all along this entire thing, because we're going to have other forces changing the shear as we go along it. And same thing for moment. So these lines here represent the different sections of where we took our cuts. So the first thing we're going to want to look at is left of A. And so our formulas for that, we'll start with the shear. Our formula for the shear left of A is just that shear is equal to negative 20. And so we're just going to draw in a line here, negative 20. And this just shows that our shear is going to be consistent through this whole section here. The next thing we're going to worry about is our shear for here, for the middle part. And so we're going to get that shear is equal to 120 minus 4 times x2. Now, we're going to start right here where x2 is going to be equal to 15. We're not going to start from the left edge where x2 is. Essentially, this formula only works for when x2 is between this 15 and this 45 feet. So when x2 is equal to 15 feet, we end up getting that the shear is going to be equal to 60 feet. Or not, I'm sorry, not 60 feet, 60 kips. A positive 60 kips. And then we're just going to go down and we're going to calculate along other ways. So if we were to calculate where our shear was when we have 30 feet right here in the middle, we end up getting that our shear is going to be 0. And that makes sense because it's 120 minus 4 times x2. So when x2 is equal to 30, it's 120 minus 120, it's equal to 0. And then for the right end, if we substitute in 45 feet for that, we're going to end up getting negative 60. And in between, if you guys can see, since this is just a first order formula, as in we have the y-intercept and the slope, it's going to be a straight line acting downward. So the slope of this line is going to be the negative 4 that we had from our formula. And then lastly, we're going to look at our last formula here, which we get that the shear is just a positive 20 kips. So we'll go ahead and draw a line up here to 20. And that's pretty simple. How much time do you guys have left? 10 minutes? Okay. So this is our shear here. And one thing with these is you're always going to want to label what the diagram is, and you're always going to want to give units. So we've got the shear here, and the unit is in kips. That's going to be, writing our labels for these diagrams is going to be a good 1 or 2 points on the exam at least. And it's really easy points there. So make sure you include that. And then you also want to include, obviously, all of the values, or all the big values on here, where we have a maximum or a minimum. So we have the negative 20 here and the 60 here. You've also got the 0 here, and you're going to want to label where these are acting. So if we go ahead and find here, the 0 here, as we found, is going to be equal to when we're right in between this. So we're going to just draw in 15 feet there. So that's our shear diagram. We can go ahead and move on to our moment diagram. So our moment diagram is going to be given in kip feet. And again, we'll go ahead and look at the formulas that we have here. So our first formula is that moment is equal to negative 20 times the distance. And so we'll start from 0 here because there's no y-intercept. And when we go through negative 20 to 15 feet, we're going to end up getting negative 300. And because we got just a simple slope here, it's going to be negative 20 is the slope, and it's going to be a straight line. So go ahead and draw that in. Okay. Next thing we got is this formula here, which is really ugly, but we're essentially going to just solve for what it is at the beginning and at the end, and then we're also going to want to solve for it right here in the middle. So if we solve for what it is at the beginning, I'm not going to go ahead and show you the work for that. I'm just going to tell you that at the beginning, we get that it's negative 300 feet. And then at the end, we get that it's also negative 300 feet. And in the middle, we're going to get, or when we get x2 is equal to 30 feet, right in the middle there, we're going to get that it's 150. Now this is where you kind of have to just draw in a shape here. As you can see here, we've got an x squared, and it's a negative x squared, which means that we're going to have a parabola that's going to be pointing downward. So our shape is going to kind of follow that shape there. And then lastly, we're going to have our shear force, our bending moment for the right end here we got as negative 1200 plus 20 times x3. And again, you're going to solve for it when x is equal to 45 feet here. And so using that, we get that it's equal to negative 300, as it should be. And then we're going to add our slope in here. And when we solve for it, at the very end of this, we're going to end up getting it's equal to 0. And it's a positive slope, so we're just going to draw it in going positive. There. And it ends up at 0. So those are our shear force and our moment diagrams here. There's some other odds and ends that you're going to want to include in your diagrams as well. So when we have lines like this and curves like this, you're always going to write in what order the formula was. So if that's not quite making sense, if we were to look at our shear force for this middle part here, we get that it just has negative 4 times x. That essentially means that it's a first order polynomial because it's just a straight line slope. So you're going to want to draw a little label here that says first order. And then off to here, hopefully, you could write in that these are constant. That's not entirely necessary. Hopefully they should be able to see that it's constant, but if you want and want to be safe, you can always label in your straight lines as constant. And then if we were to look down here at our shear, we get that to the left of A, it's again first order because it's just a coefficient times x. And that's kind of the same thing for this last one. And then if we look at in between here, because we have that x squared, it's going to end up being second order. All right? And those are just kind of some odds and ends that you'll learn. You'll learn more about what to include in lectures, hopefully. So if I missed anything, which I very well could have, they'll kind of show you that. They're also going to show you a different method where just by looking at this diagram here, you're going to be able to determine what these formulas are going to look like without having to make cuts in all the different parts. You're just going to be able to visualize it. So that's kind of exciting, I think. I think it's kind of a satisfying thing to learn. This kind of gets to be a headache after a while with all the different formulas and cuts and all that we have to make. So when you guys learn that, it's going to be pretty helpful. But that's all I have for you guys today. Hopefully it made sense to you guys and it wasn't too boring or whatnot. But anyway, thank you guys for coming, and I'll see you guys later.